Hello students! Today we begin our transition towards a new chapter, Single Order Differential Equations. And don't worry, we will keep the integration practice series alive with regular uploads. To kick this off, let's start by learning about the methods used for solving single order differential equations. The first method is direct integration. This happens if we have a function in the form dy over dx equals f of x. In this, we multiply dx on both sides. Remember that for integration to take place, our dy and dx need to be in the numerator. We can integrate this then to get y equals capital F of x plus c, where capital F is the antiderivative of small f. The second method can be applied if an equation is separable, meaning it can be written as two functions. An example is if you are given dy over dx as g of x times h of y, then cross-multiplying gives dy over h of y equals g of x dx. This way we have all the y terms on one side and the x terms on the other and can be integrated next. What if the equation is homogeneous? Meaning an equation takes the form dy over dx equals f of x over y, or alternatively, dy over dx equals f of y over x, meaning that f is a function containing both variables. The most common method to solve this is using the substitution v equals y over x. Then the function just becomes f of v. Now we look for another way to write dy over dx, which is basically taking the derivative of y with respect to x. And from the relation we established earlier, we know that y equals v times x. So we use product rule for the derivative, which gives x times dv over dx plus v times 1. Now we can put our two dy over dx expressions equal and rearrange to have our two variables separate. Then take the reciprocal on both sides to get dv and dx in the top, and this can be integrated. An exact equation is one given by the form m of xy times dx plus n of xy times dy equals 0. And we have a function f such that the partial derivative of f with respect to x is m and with respect to y is n. Then the equation is said to be exact. And if we plug these into the top equation, this is just chain rule that just tells us that df is 0, meaning f is just a constant. Now to solve this first, we check if the equation is exact. If the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, then the equation is exact. Now we need to find the function f. We can do this by integrating one of our terms. Let's say we integrate m. That will be with respect to x due to the dx here. This gives us f of xy plus c of y. The constant here depends only on y. If we integrated n, then the constant would only depend on x. Now we take the partial derivative of this with respect to y, and that is equal to n, as we stated earlier. We then solve for c, which is the constant of integration, and this is equal to f. Time for the last method, integrating factors. Given an equation in the form dy over dx plus p of x times y equals q of x. If this equation was exact, then we could just integrate both sides and find the answer, but most often that is not the case. An integrating factor is a function called mu of x, which we can multiply with both sides of the equation to make it exact. Now we focus on the left side. We identify that this is just product rule, or the derivative of mu x times y of x, which gives mu x times y prime x plus mu prime times y. Comparing tells us that mu prime is just equal to mu times p. We can divide mu on both sides in this equation and integrate both sides. Evaluating the right side gives ln mu x. Then inverse natural log can be taken on both sides to give us the integrating factor as e power the integral of p of x. Now, to solve questions, we can identify the integration factor and write the terms as a product inside the differentiation sign as done here, then integrate both sides to get the answer. We will solve examples for all methods in upcoming videos, so no need to worry. Last lecture, we looked at an equation given by the form dy over dx plus p of x times y equals q of x. When we solve this equation, we get a solution which can be written as the addition of two terms. The general solution can be given as y equals y homogeneous plus y particular. Before solving a question, let's understand this further. We consider the case that q is 0. This makes the equation homogeneous. To solve this, we take the p times y to the other side and cross-multiply to get the y terms on one side and the x terms on the other. This way we can integrate this. The left side is evaluated to give ln y, and to find y, we take inverse of ln on both sides, which tells us that the solution to the homogeneous part is given as e power negative, the integral of p, and the particular part can be understood through examples. Let's do an example to reinforce this concept. Given the equation, dy over dt plus 4y equals 8. The homogeneous part will be when the left side equals 0. Now we can directly compute the solution using the formula that we derived, so it will be e power negative integral of 4, which gives it as e power negative 4t plus c. And due to the exponential properties, this can be written as e power negative 4t times e power c, which is just a constant that we can call a. We just found the homogeneous solution to the equation. Now we need to find the particular solution related to this case, which is when the equation equals 8. In this case, it can be found using observation. We need a value of y that makes the left side equal to the right side. The right side is just a constant, 8. Then we guess a constant for the value of y particular as well. yp equals 2 fits the requirement. As the derivative of 2 is just 0, so the first term here is 0, and 4y becomes 4 times 2, or 8. Therefore, our complete solution is a times e power negative 4t plus 2. Let's do some examples today to reinforce the method of direct integration. The examples will get more difficult as we go along the video. We will have another video later with more difficult questions. We have the first equation as dy over dx equals 3x squared. Our first step is to have both dy and dx in the numerator. So we multiply both sides with dx. Then we can integrate both sides. The left side becomes y, while the right side gives 3x cubed over 3, where the 3's can cancel out to give x cubed plus c, which is the constant of integration. We just need to write c on one side because even if we put constants on both sides, say a and b, then we just simply subtract a on both sides and suppose the constant b minus a as c. Moving on to a more difficult example, dy over dx equals x squared y. We cross-multiply, or we mean that divide y on both sides and multiply dx on both sides. This gives 1 over y dy equals x squared dx. Then integrate both sides to get ln y equals x cubed over 3 plus c. Take natural log inverse on both sides to get the final answer y equals e power x cubed over 3 plus c, which can also be written as e power x cubed over 3 times e power c. E power c is just a constant which we can rename and call d, so the answer can be y equals d times e power x cubed over 3. Time for a difficult one. Y prime squared equals 6 over 4 minus 4x squared.
Damn, that is difficult.
You have been awfully quiet this video?
Just learning for now.
That's good. Back to the question. We can write the left side as dy over dx whole squared, and for the right side, take 4 common in the denominator. Then we can simplify the 6 over 4 to 3 over 2. Moving on to take the square root on both sides. Then we can multiply dx on both sides to bring all the x terms to one side. Before integrating, the 3 over 2 can be written separately, so we will do that. And in the numerator, we just have root 1, which is 1. And now we integrate. The left side is just y.
And the right side is sine inverse.
That's right. So the final answer is y equals root 3 over 2 times sine inverse of x plus c. Welcome back, everybody. Time for 3 difficult direct integration questions with initial or boundary conditions. First question, dy over dt equals ln 4t, with the boundary condition y equals 2 when t equals 1/4. First step is to multiply dt on both sides. Then to make this look simpler, use u substitution with u equals 4t du over dt equals 4 and dt equals du over 4. We plug this back in. Then, evaluating the left side gives y, and the right side is the integral of ln u, which can be found using integration by parts. To give u ln u minus u plus c, we can back substitute the value of u to get the equation in terms of t. Then distribute the 1/4 inside the brackets. Finally, to find c, we plug in the boundary condition, which gives 2 equals 1/4 ln, 4 times 1 over 4, which is 1 minus 1 over 4 plus c. ln 1 is just 0, so c equals 2 plus 1 over 4, or 9 over 4. Plugging this back in gives the answer, y equals t ln 4t minus t plus 9 over 4. The next question is a separable equation. X times x minus 1 times dy over dx equals y times y plus 1, with the boundary condition y of 2 equals 2. We can begin by cross-multiplying. Let's keep the y terms on the left side and the x terms on the right. Then we can integrate this. However, there does not appear to be a clear-cut way to integrate this. Therefore, we use partial fractions. To learn more about integrals and how to choose which method to use, make sure to visit our integration practice series. Let's do partial fractions for the left side first. The expression can be rewritten as a over y plus b over y plus 1. Multiply both sides by y times y plus 1. We can solve this by choosing y values that help simplify the expression to find one of the constants. Choosing y as 0 gives a equal to 1, and choosing y as negative 1 gives b equal to negative 1. We do the same for the right side. An equivalent expression is c over x plus d over x minus 1. Multiply both sides by x times x minus 1. First choose x as 0 to get c as negative 1, and choosing x as 1 gives d equal to 1. Now we have expressions on both sides which can be integrated. Evaluation gives us ln y minus ln y plus 1 equals negative ln x plus ln x minus 1 plus c. Both sides can be simplified due to the logarithmic properties. If we have a subtraction sign between two ln terms, then they can be written as a single ln term with the values inside the brackets being divided. The boundary condition can be plugged in. Both x and y are equal to 2. This gives ln 2 over 3 equals ln 1 over 2 plus c. Yielding the value of c to be ln 4 over 3. This can be plugged back in. Then we have a plus sign between the two ln terms on the right, so the insides will multiply. Then log inverse can be taken on both sides to get rid of ln. And some basic algebra at the end gives us the answer. Y equals 4x minus 4 over 4 minus x. Time for the most difficult question for today. Cos power 4 of x times dy over dx equals sine cubed x, with the condition that y equals 8 over 3 when x equals pi over 3. As usual, we start by cross-multiplying. Now integrate both sides. The left side yields y, while the right side, does not look that good. However, we recently taught a trick for solving similar-looking integrals, so make sure to check that out. There are a couple of methods to solve this, but we will use the best, most simple method, starting by rewriting this. Sine cubed over cos cubed can be written as tan cubed, whereas the leftover cos in the denominator can be written in the numerator as secant x. Here we have trigonometric terms being multiplied while having a power greater than 1. Therefore we use trigonometric identities. Tan squared x is equals to secant squared x minus 1. Which enables us to use u substitution. Choosing u as secant x gives du over dx as secant x tan x, and dx as du over secant x tan x. Then our secant and tan terms cancel out, leaving us with the integral of u squared minus 1, which is evaluated to gives u cubed over 3 minus u plus c, and back substituting u to get secant cubed x over 3 minus secant x plus c. Lastly, the condition is used. Cos pi over 3 is just 1 over 2, therefore secant pi over 3 is 2. So 8 over 3 equals 8 over 3 minus 2 plus c, therefore c equals 2. So the final answer is secant cubed x over 3 minus secant x plus 2. Hello everyone, time to practice a homogeneous equation. We have the equation dy over dx equals y squared plus 2xy over x squared. Throw back to our video on the different methods. We mentioned that homogeneous equations can be written as a function of y over x. So we need to begin by rewriting the question. We can write the two terms separately, meaning y squared over x squared or y over x whole squared, plus 2xy over x squared, where the x can cancel out to give 2 times y over x. We introduce a new variable, v as y over x, or y equals x times v. Next step is to take the derivative of y with respect to x. And yes, we are talking about this equation. We will implement the concept of implicit differentiation to get dy over dx equal to 1 times v plus x times dv over dx using product rule. This is one expression for dy over dx, and the other one was the one we rearranged. We plug v into that to get v squared plus 2v. We can put the two expressions equal. Now to simplify, subtract v on both sides. Then divide dv on both sides.
Wait, we have a problem. The dv and dx are in the denominator.
Oh, that's fine. We can take the reciprocal on both sides or flip them. Now they can be integrated. The left side is ln x, whereas the right side. Seems like we need to use partial fractions. Let 1 over v times v plus 1 equal to a over v plus b over v plus 1. Multiply both sides with v times v plus 1, giving 1 equals a times v plus 1 plus b times v. Now choose v as 0 to get a as 1, and choose v as -1 to get b as -1. Now we can integrate this to get ln v minus ln v plus 1 plus c. The ln terms can be combined. An ln inverse can be taken on both sides, which gives x equals v over v plus 1 times e power c. We know that e power c is just a constant, so for simplicity, let's call it d. D can be divided on both sides. Then we can plug back the value for v. And to get the result, we need to make y the subject. Some basic algebra will do the trick. Begin by cross-multiplying. Expand the brackets on the left side. Then multiply both sides by x. Then move all y terms to one side. Take y common and divide the term in the brackets, or x minus d, on both sides to get the final answer, y equals negative x squared over x minus d. Welcome back, everyone. Before solving an exact differential equation, we will practice how to find out if an equation is exact. We need to keep the general form in mind, which is m dx plus n dy, where m and n are functions of x and y. And the condition for an equation to be exact is that partial m over partial y should equal partial n over partial x. Let's start with the first example, x dy plus y dx. By comparison, we get m equals y and n equals x. We take the partial derivative of m with respect to y, which gives us 1, and the partial derivative of n with respect to x, which gives us 1. Since they are equal, then this equation is exact. Let's try another example, x dy minus y dx. Here, m equals negative y and n equals x by comparison. So take the partial derivative of m with y to get negative 1 and n with respect to x to get 1. They are not equal, so this is not an exact equation. Time to add a bit more complexity into the questions. Check the equation 2x cubed y times dy plus 3x squared y squared dx, where m will be 3x squared y squared, and its partial derivative with y gives 6x squared y, and n, which is 2x cubed y, taking its partial derivative with respect to x, is 6x squared y. Therefore, it is an exact equation since they are equal. Time for one last one. Let's make it more difficult. We have the equation 2 sine x cos 2y dx minus cos x sine 2y dy. Here, m is 2 sine x cos 2y and n is negative cos x sine 2y. Take the partial derivative of m with respect to y. That gives negative 4 sine x sine 2y. Then take the partial derivative of n with respect to x. That yields sine x times sine 2y. Since the answers do not match, this equation is not exact. Let's solve the equation 2xy cubed plus 3x squared y squared times dy over dx equals 0. We learnt that an exact integral is one given in the form m dx plus n dy equals 0, where m and n are functions of x and y, which means we need to rearrange the equation. Take the 3x squared y squared times dy over dx term to the other side, then multiply both sides by dx. Now the term can be taken back to the left side. This way, we have the equation in the proper form. So, we can check whether this equation is exact or not. The condition is that the partial derivative of m with respect to y should equal the partial derivative of n with respect to x. Comparing the equation to the general form, we get m as 2xy cubed and n as 3x squared y squared. Partial m over partial y gives 6xy squared, and partial n over partial x gives 6xy squared too, which means the equation is exact. All right, we need to find a function f such that partial f over partial x is m and partial f over partial y is n. In other words, we integrate one of our terms in the equation. Let's integrate the n term. That would be with respect to y because of the dy here. Integrating gives 3x squared y cubed over 3 plus c of x. The 3's cancel out. We also know that f is a constant, so this equals to c, another constant. We can incorporate the other constant into this too to get just x squared times y cubed equals c. Divide x squared on both sides, which makes y cubed equal to c over x squared. Take the cube root on both sides, which makes the left side y, and expand it on the right side to get c times x power negative 2/3. That is our final answer. It is to be noted that the constant changes here, as we are subtracting another constant from it. And here as well, since we are taking the cube root of it. It is always a good thing to make a note of it, or you can choose a different letter for it. All right, today let's learn about integration factors. It is a method to make differential equations exact. We will solve the question dy over dt plus 4y equals 8 using 3 different methods. We need to begin by identifying the integration factor. In the first video in this series, we talked about the general equation given as dy over dx plus p of x times y equals q of x. Since our variable is t, let's just change it to that in order to avoid confusion. We derived the method on how to find the integration factor, mu, and that came out to be equal to e power, the integral of p of t dt. We can identify the function p as 4 in this example, and integrating 4 gives 4t, so the integration factor is e power 4t. Next step is to multiply this on both sides of the equation. Then to solve it, we have 3 methods. First, let's do it using the exact equations method, or the one we used last video. So we need to get it in the proper form, which requires us to take the 4y e power 4t term to the right side, and then multiply dt on both sides. Then we can take this term back to the left side, and we can see that it is in the perfect form. We identify the term m as 4e power 4t times y minus 8e power 4t, and the term n as e power 4t. If you want to confirm if it is an exact equation or not, you have to take the partial derivative of m with respect to y, and the partial derivative of n with respect to t. These both come out to be 4e power 4t, which confirms that the equation is now exact. Now, to find the solution function, we integrate either m with respect to t or n with respect to y. For the sake of simplicity, let's integrate the n term. That gives e power 4t times y plus c of t, and the function f is a constant too, which we can call c. The two constants can be combined to give a new constant, which we call b. Therefore, b equals e power 4t times y. The e power 4t can be divided on both sides to get the solution y equals b times e power negative 4t. Next, we can do it using the integration factor method. Personally, I prefer using this method or the third one, which we will talk about later in the video, as they are much simpler. Back to the question, we identified the integration factor and reached this equation previously in this video. Now, how we solve this is by setting up the left side as a term being differentiated. This will always be the derivative of y times the integration factor. You can also check this if you want, using product rule. It will come out to be the same thing. Now that we have it written as this, we can integrate. However, first multiply dt on both sides.
Wait, why is it just d on the left side?
Well, you have the y here, which multiplies with it, and essentially you can write this as e power 4t times dy. The right side is 8e power 4t times dt. We integrate both sides to get y times e power 4t equals 8e power 4t over 4, which is just 2e power 4t plus c. Divide e power 4t on both sides to get the final answer. Y equals 2 plus c times e power negative 4t.
Why is there a 2 in this answer and not in the previous one?
The answer is simple. 2 is just a constant, so basically our constant c in this case, and constant b in the last answer will differ slightly. The last method we will cover is the splitting method we used in a previous video. In fact, in that video, we did the exact same example, so make sure to check it out. Thank you, and stay tuned for the next video, where we will practice further examples using integration factors. Time to do two more slightly more complex integration factor questions. First question is y prime plus t times y equals 5 times t. The integration factor is e power, the integral of the coefficient of y, which is t dt. Integrating it yields mu as e power t squared over 2. Now we multiply it on both sides to make the equation exact. We learnt last time that the left side can be written as a derivative of y times the integration factor. As this is an equivalent expression, you can check it using product rule if you want. Next, multiply dt on both sides and we can integrate them. The left side just gives us y times e power t squared over 2, which equals the integral of 5t times e power t squared over 2. The 5 can be written outside of the integration sign. Integration here is simple if you know how to proceed. We have a difference of powers of 1 between the two t's. Therefore, u substitution is a good option to start with. Take u as t squared over 2. du over dt gives 2t over 2, or just t, and dt is du over t. We can plug this back in. E power u times t times du over t. We cancel the t's, giving the integral of e power u, which is just e power u, and back substituting, it will be e power t squared over 2 plus c. Finally, we can divide e power t squared over 2 on both sides to get the final answer, y equals 5 plus c times e power negative t squared over 2.
If we use any of the other methods, can we make the solution easier?
Yes, the splitting method makes this way simpler. First, take the homogeneous part of the equation. That is when we say the right side is just 0. Take the ty to the other side. Then divide y and multiply dt on both sides. And simply integrate both sides to get ln y equals negative t squared over 2 plus c. Take ln inverse on both sides to get the answer, y equals b times e power negative t squared over 2, where the constant b equals e power c. The answer could also have been computed directly, as we derived it in our previous video where we highlighted this method. We showed the solution equals to e power negative integral of p, which is exactly what we got. The particular solution here can be found by just intuition. We can substitute y as 5 into the equation, which will make both sides equal. The derivative of 5 is just 0, and we have 5t on both sides, confirming that 5 is the particular solution. Both methods therefore yielded the same answer. Feel free to choose any one of them you prefer. The second question we will be solving for integration factors is y prime minus y equals t squared. The coefficient of y is negative 1, which makes the integration factor equal to e power integral of negative 1 dt, or evaluating it to get e power negative t. Multiply it on both sides of the equation, and if you have watched the previous videos, then you already know we can write the left side as the derivative of e power negative t times y. This makes it easier for us to integrate. The left side, integral and derivative cancel out, giving e power negative t times y, while the right side is the integral of t squared times e power negative t. This can be integrated by parts, as we can choose u as t squared and dv as e power negative t. This makes sure the power of t decreases by 1 inside the integral. Therefore, in this question, we will have to do integration by parts twice, which will result in negative e power negative t times t squared plus 2t plus 2 plus c. Multiply e power t on both sides to yield the answer, y equals negative t squared minus 2t minus 2 plus c times e power t. Now, to use the easier splitting method, put the right side equal to 0. The homogeneous part can be directly integrated as it equals e power negative integral of the coefficient of y, which is negative 1. Yielding e power t plus c. When using this method, make sure to not forget about the constant here. Usually we bring it up after, but this time we are using a different approach, so we include the constant here. Then we can also write this as b times e power t, where b equals e power c. The interesting part in this method is finding the particular solution. The right side shows us a t squared term. Therefore, we come up with a particular solution in the same form. Let's say y part equals at squared plus bt plus c, and y prime will be 2at plus b. Now we can plug these into the equation given in the question and compare the different coefficients for the terms, giving a as -1 to a minus b equals 0, which gives b as -2, and b minus c equal to 0, giving c as -2. Therefore, y part is -t squared minus 2t minus 2, and the general solution being b times e power t minus t squared minus 2t minus 2.